So let's see this theorem now in action. You will often be asked, I mean, this is a standard problem. You have some series of things depending on x, you define a function based on that, and you're asked to show that this defines a continuous function, R to R. Okay, so proof or solution of this. Well, this has two parts. This problem really defines and continuous. Defines means that this is a well-defined expression, so that the series converges. I mean, you can write a series, you can write anything you want. I mean, I can write sum n equals 1 to infinity of minus 2 to the n, but this, I mean, that you can write it, it doesn't mean it doesn't have to have any meaning. So defines means it has some meaning. In particular, other words, it means that it converges. So the first check should be that it converges. Well, so by Weierstrass M-test, we get convergence, uniform convergence. Why? Because, well, sine of nx over n squared, absolute value, is less than or equal to 1 over n squared is equal to mn. By setting mn as follows, now n equals 1 to infinity of mn is less than infinity by the p-test. So we get that converges uniformly and the limit function is continuous. Okay, done. So it shows that this Fourier series, it's called a Fourier series because it involves sine nx. We'll talk a little bit more about them in about hopefully 2 weeks. I mean, I don't know what that function is. It actually has probably a nicer expression, but it's just something. So this defines a continuous function on the space. Now, last time I mentioned you a different series if you had a different power of n, just one n here. But okay, that if you don't have anything else there, then Weierstrass M-test does not apply because the upper bound would be 1 over n. But if you put a random coefficient here, in one of the examples last time I mentioned, then actually you do get something convergent. So you actually get something that these converge to a continuous function. These the partial sums converge to a continuous function. But that's much harder and way beyond this class. So you could think that, okay, the theorem is not sharp. But I mentioned that, so there are other series and other interesting things that happen. So that's one of the reasons you might be interested about these Fourier series and looking at their convergence. But let's combine two things, what we did on Monday and what we did today. This is a very quick thing. Again, if you put a higher power, n cubed, then you actually get that you are continuously differentiable. In particular, you have a derivative which is continuous. Okay, why is this? You have to apply the Weierstrass M-test twice. So first for f, so you have that with fn of x is equal to sine nx over n cubed, then we have, and fn of x is less than or equal to mn, which we define as 1 over n cubed. As above, the series converges uniformly by M-test to continuous function. Okay, but what about the derivative? This requires us to look a little bit at Monday. So if you look at, so what we have is that Sn if actually the sequence of partial sums is converging, well, it converges pointwise to f of x as n goes to infinity. But if you take the derivatives of these, it is itself a derivative series. And what is the derivative series? It's cosine nx over n squared. Now, by M-test again, the series n equals 1 to infinity, cosine nx n squared, let's define this g of x, is continuous. And you would use, I'll skip a few steps, mn would in this case be 1 over n squared. So you get that this series converges to a continuous function, and Sn prime x, so the derivatives converge uniformly to g. So now the derivatives converge uniformly to g. Therefore, by theorem from the beginning of class, what we have A is that the derivatives are continuous. The assumptions here are A. We have uniform convergence, and also the other assumptions are verified. Therefore, from the theorem at the beginning of the class, we get that f prime is equal to g, and g is continuous, which is exactly what we wanted to show. Okay, sorry for going 2 minutes over, but this is the end of the lecture. I'm happy to discuss any questions that you may have.